Swayam Prabha. Digital India. Educated India.
Hello. So welcome to the second lecture in astrochemistry. In the last class, I had introduced you to the field of astrochemistry and using two examples, one redox equation and another acid-base reaction, I had emphasized to you about how much more chemistry we can learn about what's happening on Earth vis-a-vis learning about how molecules behave and their chemistry in space. This is something we looked into in the last lecture. Now in this lecture, we'll continue along the same thing, and instead of taking the reaction of small simple molecules, let us take the reactions of organic molecules, right? So consider some organic chemistry happening in space. And what does that have to teach us about molecules behaving in space? Okay, let's consider, for example, this very simple reaction. Let's say, on Earth, we carry out this reaction at about 300 Kelvin, which is close to room temperature. I carry out this reaction. What do you think is going to be the product? The product is going to be what? The product is going to be acetaldehyde. Okay, you may be wondering now, hey, I just added water and I learned from my high school chemistry that water adds across the multiple bonds. So the product I should be getting, shouldn't it be something like, if I simply consider water dissociating as OH and H, OH minus and H plus, shouldn't I be getting this, right? But instead, how did this become this? What's happening here? Well, this should be your first line of thought, that I must be getting this compound containing an alcoholic group and a double bond called as an enol molecule. However, what I ended up getting is actually acetaldehyde, right? Which is an aldehyde. What's happening here? How did this expected molecule, how did this expected molecule become this? Well, the answer is, as most of you would have already guessed by now, this is an example of keto-enol tautomerism. Now, what's happening is that indeed, at 300 Kelvin, once acetylene reacts with water, you indeed do form the enol. The enol formed tautomerizes to give you, so you have the flow of electrons from here to give you the aldehydic form, and this abstracts the proton from here to eventually give you acetaldehyde. Okay, right? Now, you may be taught in organic chemistry that because this species, the enol species, contains a highly electronegative OH group and a double bond on the same carbon atom, enols are unstable. Why? Why? Because it has the highly electronegative OH group and C double and an electron-rich region, on the same carbon atom. So perhaps owing to electronic repulsion, this is highly unstable, and that is relieved in this molecule of acetaldehyde. This is our understanding, right? Yeah. Now this is what is known on Earth about this reaction. However, notice a subtlety. When we say that this reaction is happening on Earth, the temperature we are talking about is 300 Kelvin. Okay. Now, a lot of regions in space are extremely cold. Note this point. Okay, right? Now, how cold does cold get? Any suggestions? Any idea as to how cold exactly does cold get? We are talking about a temperature less than 10 Kelvin or even 3 or 4 Kelvin in some cases. So this is how cold one can actually get in space, in some parts of space. Mind you, I'm not talking about all the regions of space. Now, under these conditions, under these very cold conditions, this transformation, it was experimentally found out, okay, right? Experimentally, it was found out approximately, I think in the early 2000s or in late 1990s, that the rate of this specific, the enol to keto transformation, this particular transformation, right, was found out to be favoring the enol, was found to be favoring the enol at temperatures less than 10 Kelvin. So indeed, if you were to, if for example, water were to be added to acetylene in space, you would end up getting the enol in the low temperature regions and not the keto, right? So what we understand about from this chemistry in space is that molecules touted to be unstable can be obtained in space. For example, it is common knowledge, it is common high school or undergraduate first year knowledge that the enols are highly unstable, with the exception of some molecules such as phenol, due to the concept of aromaticity therein, right? The enols which are highly unstable, right? But at very low temperatures, which is the condition present in space, in regions where such reactions can happen, you can actually isolate molecules which are said to be unstable, right? Isn't it fascinating? So we understood that reactions which happen on Earth, right, the modified versions happen in space. And not just that, molecules which are conventionally perceived to be unstable on Earth, even they can be formed in space. Okay, right? So this is yet another fascinating aspect of space, and by studying the chemistry of molecules in space, right, we understand and discover so many more new principles in fundamental chemistry. I will highlight just one more example. This shall be a last example. Now, consider this molecule. This should also be from organic chemistry. Consider the molecule of now, this is HC double bond O, CHOH, CH2OH. What is this? This is nothing but the dimer of formaldehyde. So you have like two molecules of formaldehyde coming together and dimerizes to form this. This molecule itself is called as glycolaldehyde. Now, on Earth, okay, right? Let us assume that you want to order a bottle of this molecule. You want to order a bottle of this molecule. You would go to some company which supplies this molecule to you, and you would invariably, and then you try to find out the molecular weight of the compound you get. You will be startled to notice that on Earth, now on Earth, right, you will be startled to notice that if you determine the molecular weight of the compound you get from the chemical company, it will be twice the molecular weight. Let's call this, glyceraldehyde small g. Sorry, glycolaldehyde small g. Twice the molecular weight of G. Why did that happen? How did you end up getting twice the molecular weight? You ask for something and the chemical supplier is giving you something else. How is it possible that you get twice the molecular weight? And which then means that you don't even get this compound, right? Well, as it turns out, what's happening on Earth is that this molecule, glycolaldehyde, which I'm calling as G, it dimerizes readily. Well, and so therefore, you have two of these molecules combining to predominantly, exist in a linear structure. Okay, right? If I'm correct, there must be an OH here and there must be an OH here. Okay, right? So I think this is the dimeric structure, one of the dimeric structures possible. So this molecule dimerizes to give this, and therefore the chemical bottle that you get in hand, it actually corresponds to this because it readily dimerizes, and we're again talking about temperatures of 300 Kelvin. But again, going back to space, where there are a lot of regions with very low temperatures. There are lots of regions in space with very low temperatures. The molecule glycolaldehyde right? You can get this molecule in its pristine monomeric form because you obtain it at low temperatures. Now, what is in space? So you can get the monomeric form itself. Now, what is the message I want to convey through this example? I want to convey through this example that some unwanted chemistry, or not exactly unwanted chemistry, but you can obtain molecules in their pristine form, which is otherwise not possible in the chemistry happening on Earth because of phenomena like dimerization, etc., etc. You could get molecules in their pristine form and avoid further we discussed 4 examples, correct? The first example we saw in the previous class was a redox reaction. The next reaction we saw was an acid-base reaction, and then we looked into 2 organic examples from organic chemistry about how the equilibrium of the keto-enol tautomerism can be shifted one way. And lastly, we looked into this molecule, that is glycolaldehyde, and how we can see that the conditions in space prevent further reaction of some molecules, and we can obtain the molecules in their pristine state itself. Now, let me just sum it all up. Recall where we began this conversation. We began this whole conversation with the idea of why study molecules in space, right? which is basically why I study astrochemistry. The first one was that using the example of the redox equation, we understood that reactions in space can be modified from what's happening on Earth. Next, we chose the example of an acid-base reaction, and we understood that you don't need a solvent. You don't always need a solvent for chemical reactions, and that molecules behave unexpectedly. For example, H2 was shown to be a base, right? H2 on Earth is never a base. So molecules behave unexpectedly. From the third example, that is the example of the keto-enol tautomerism, we understood that the relative stabilities of molecules can also get altered in the interstellar medium. Relative stabilities of molecules can get altered in space. And lastly, we looked into the idea of the molecule called as glycolaldehyde, and this tells us that, hey, it's not just modified reactivity, some further reactivity of monomeric species can also be avoided in space. So, using these 4 examples, by the way, all these 4 examples were actually put forth in a beautiful Journal of Chemical Education article by Dr. Reggie Hudson of NASA to illustrate the beautiful things we can learn and enhance our knowledge of fundamental chemistry by studying molecules in space. Okay, so this is one reason. You may ask me the next question. I don't actually want to study about chemistry even. Why should I care about chemistry? Okay, let molecules behave the way they do, right? The conditions in space are different from the conditions on Earth. So therefore, it's natural that their behavior will be different. What is yet another reason why I need to study molecules in space? The answer would be that here is a profound answer. Here's a profound applied answer, which is not just about studying chemistry or learning more new chemistry. It's because studying molecules in space gives us the opportunity to study the possible origin of life itself. This is something very cool, right? And unexpected. But notice the word possible. No one can, of course, state anything with certainty yet about the origin of life itself. However, one can always make tremendous assumptions about how exactly life originated, and did it originate on Earth only? Recall, all of us are so very interested about aliens. We are so very interested to find out whether life is possible on other planets. For example, ISRO had a mission to Mars, Mangalyaan, and NASA is also constantly monitoring Mars for traces of markers of life such as water, etc., etc. So, can we actually, worry about understanding the possible origin of life itself by studying molecules in space? Isn't the idea fascinating, right? But how and what clue do we get? about the origin of life by studying molecules in space. The space is space and Earth is Earth. What clue do we get? The answer is that in space, we have a nursery of small molecules such as H2, for example, ammonia, HCN, right? H2, NH3, HCN, formaldehyde, thioformaldehyde, etc., right? Which are all the building blocks. These small molecules, these extremely small molecules are going to be the building blocks for larger molecules, such as, for example, you take NH2, right? What is this molecule? This is glycine, okay, right? So for molecules such as glycine, alanine, etc., etc. Now, what are these? These are the small biomonomers. What's a monomer? This is the monomeric unit of a larger peptide or a larger, much larger molecule containing repetitive units of these molecules, for example. And you have, for example, sugar. Take, for example, glucose. Glucose is O6, right? What does glucose contain? Glucose can be typically represented as, without worrying about the stereochemistry itself, glucose can be written as, it's a 6-carbon chain. I'm writing the linear form of it. Right? So this is the linear form of glucose. If you think about glucose, it is nothing but formaldehyde times 6. C6 H12O6 is nothing but CH2O times 6, right? So this is an oligomeric unit of this formaldehyde, right? So all these small molecules are precursors to the biomonomers. And why do we care about these molecules? Because they are what is found in our body, right? Yeah. And these larger units, such as the amino acids, the carbohydrates, some nucleic acids, nucleic acids, etc., etc. In some composition, they give rise to larger units such as cells, and then you have like layers, you have cells, and taken together, they all become us, right? So overall, the amino acids, carbohydrates, etc., they give rise to life itself. So by studying the most fundamental units, which are all molecules found in space, right? And by studying their evolution, we understand how life could have originated. But notice that it is only a could have originated, because life requires functionality. We are only talking about a structural level. But by studying molecular evolution, the evolution of molecules in space, followed by what happens in planets, we could eventually get a clue about how the function of life emerges. Okay, right? So overall, there are two objectives of studying molecules in space. One is to understand chemistry itself better. And that, of course, has numerous applications in various fields. That's one thing. And the other one is to understand the possible origins of life itself. And by studying the possible origin of life, hey, we can easily see how is it possible to live in Mars? How is it possible to live in, let's say, Moon? People are already talking about making tourism, enabling tourism on satellites such as Moon, and perhaps, like life on Mars. We can easily think about it. Of course, executing it is a whole new paradigm. However, with a knowledge equipped with the chemistry happening on space, we can think about problems which have evaded us so far. Okay, right? On that note, I think I shall cut it short here, and I shall begin from the next class. So we have currently looked into the concepts of what astrochemistry is, and by using some examples, I illustrated to you the relevance of astrochemistry in enhancing a knowledge of chemistry itself. This was followed by giving you some molecules which have been found in space, and how they are the precursors to the various molecules that life itself is made up of. Okay, right? In the coming lectures, we shall be answering a lot of interesting questions I have not even touched upon. See, for example, I keep telling you that these molecules are found in space. For example, H2 is found in space. But did I actually go and see it? Who saw the molecule in space? How is it possible to go in space? How do you observe the molecules? So, in the rest of this class, right? In the rest of this course, by class I mean the course, we shall be looking into how molecules are observed in space. We shall also be looking into B. How might have they formed in space, right? I mean, for example, in a chemistry laboratory, we understand how molecules are formed by synthesis. But how is it possible in space? Especially with me highlighting the low temperature in space, right? So that's another thing that I'll be talking about. Next is, what are the physical conditions of space So what are the physical conditions in space which enable this chemistry? And we'll also be looking into what are the different constituents of space wherein very different types of chemistries can happen. For example, how does chemistry happen in a region called as the interstellar medium, and how is it different from what happens in the region of another constituent of space called as meteorites? So how does chemistry happen in different parts of space? Last, so these are the things we'll be looking into, and beyond it, we'll also be looking into from space to Earth. So the examples that I gave today were all corresponding to small molecules. We started off with H2, H2 plus, and even the organic examples we gave were barely, nothing beyond 2 carbon atoms, right? From space to Earth, however, we know that we comprise of very large molecules. We contain DNA, RNA, all polymers, and the molecular weight of the polymers in our body, for example, is of the order of megadaltons, right? Yeah. So from space to Earth, right? How might have life originated on Earth? And lastly, the last topic that we might delve into as part of this lecture is some open-ended questions in the area of astrochemistry. So, with this introduction given, we shall be moving forward to our next lecture, wherein I shall be presenting to you about the constituents of space and how they enable the different types of chemistry. On that note, I thank you all for attending this lecture, and see you in the next lecture.